right, good morning. So today we are going to finish up our discussion of machine language and thereby the course, COS 217. The context here is last time we talked a bit about Arch64 machine language. So we looked at some of the instruction formats. We saw how crazy some of them can get, where you stash different bits of what you need to operate on in different parts of a 32-bit word. And today we are going to look at the remainder of this build process that we haven't talked about too much so far. So the build process, we're thinking of this as preprocess, compile, assemble, link. Preprocess, fairly simple stage. In fact, you wrote a small part of it, decomment, way back in assignment 1. Compilation is really kind of beyond the scope of COS 217. There's a COS 320 all about writing compilers, essentially translating from a high-level language, such as C, into a low-level language, such as assembly language. And then today we're going to talk about the assembler and the linker. The assembler has a much simpler job than the compiler because there is essentially a one-to-one mapping between assembly language instructions and machine language instructions. But there is kind of one tricky little bit where the assembler, as it's looking at a single assembly language file that it's trying to translate, actually doesn't have enough information to completely generate the machine language. And so its strategy is going to be to leave little notes to the linker of, hey, here's this thing that I couldn't quite finish. Why don't you help me out later on? And then the linker, which actually then has access to all of the object files, all of those .o files, as well as all of the library files, containing the standard C library code. The linker is then able to construct a final executable program and to finish the job of the assembler by filling in those bits that the assembler couldn't finish on its own. So that's going to be the process that we will go through over the rest of today. So we're going to have a model program that we look at throughout today. Here is the C version on the left. Very simple. It basically asks you to type a character. It calls getChar to get that character. And if it happens to be equal to capital A, it prints out high. Then it returns 0 for success. So, here is an assembly language version. You will recognize by now, I very much hope, all of the bits that are here in the assembly language. There is an RO data section containing the constants that we will be dealing with. In this case, it is a couple of constant strings, one being the prompt type achar, and the other one being the message hi that it outputs at the end. Then we have the text section, declares a global symbol called main, which is handy because the setup code is going to look for a function called main and jump to it to execute your C code. And then some assembly language instructions. You will recognize this as a common prologue that saves x30 on the stack. And then, sets things up, calls printf, calls getChar, compares, some jumps around, things like that. In the end, sets a return value, cleans up, and returns. Very straightforward assembly language function. So now what we're going to do is we're going to pretend that we have run the assembler on this function. So it has taken a assembly language file, a .s, and produced as output a .o file. So this isn't the final executable yet. We're not going to be able to execute that .o directly for a number of reasons, of which a big one is, what the heck is a printf? What the heck is a getChar? at the time the assembler was processing this assembly language file, it actually didn't have access to what is a printf. And it's going to be up to the linker to then kind of go fetch printf from the standard C library, concatenate it with the machine language version of this assembly language code, and then produce a final executable for you. All right, so we have run the assembler, GCC 217-C, the -C basically meaning stop after the assembler stage when you have output a .o file. And then we can start poking around at what is in this .o file. And the Unix command, the Linux command that we're going to use to do this is called objdump. Object dump, basically read the contents of a object file, a .o file, and dump them in human-readable form onto the screen. So objdump can take a lot of different flags that tells it how it's supposed to interpret what is in the .o file and what it's supposed to print out onto the screen. And we'll go over a couple of different use cases here. The first thing we're going to do is ask objdump for the contents of a particular section, namely the .ro data section of the .o file. So we pass it the full contents flag, we pass it the section ro data flag, and it tells you, well, here is what is in ro data in this .o file. And later on, when the linker runs, it's going to take the ro data sections of all of the .o files that you have, smush them together into the final ro data section of the executable that you were producing. So we're going to start, objdump lists out the contents of this ro data section. It lists it out in hex over here, and it lists it out as characters over there. So one thing to notice is this leftmost column. So that kind of looks like addresses or things like that, but it's not really going to correspond to addresses in the final executable. Because at this stage, the assembler didn't know where the linker is going to choose to put this bit of data in the final executable. So the linker just sort of started, listing things from address 0. And so what we have here are sort of relative addresses, offsets, from the beginning of the ro data section in this .o file. And later on, once we look at the corresponding output of the linker, we're going to see that the linker has actually picked a memory address where to put this data, and objdump is going to start listing actual addresses in memory, not these offsets. Okay, so we can, for now, look at the contents of this section, and we can recognize, the strings that we wanted allocated in that ro data section. Simple enough. Now, we're going to call objdump using a different set of flags, including this disassemble flag. Very useful flag. It basically tells objdump to convert machine language back to assembly language so that we can read it. And we're also passing another flag called relock to objdump, and we'll see what that refers to a little bit later. Okay, so here we are looking at the .text section. We're looking at the disassembly of it. Again, we have basically a number of columns. Here is the generated assembly language that objdump generated from the corresponding machine language, which is listed in kind of that second column from the left. Again, the first column of on the left is going to consist of offsets within the .text section. And we can actually now go through and look at what it is that the assembler did and can double check its work. Did it do things correctly? Yes? Ah, hold that question. We will get there. Just a second. The answer is at the stage where the assembler was doing it, it didn't know because it doesn't have access to printf and getchar. So we'll see how that's handled. All right, let's go through this kind of line by line. And in 1, 2, 3 lines, we will get our answer. All right, so let's start with this particular line, the first line of machine language / assembly language. We can sort of zoom in on that machine language instruction and sort of, expand it out into bits and start comparing that bit pattern to what we know about the bit patterns of assembly language instructions, such as, in this case, the subtract instruction. And we can go ahead and verify, referring back to the previous slides that we talked about on Tuesday, that this particular bit pattern corresponds exactly to this assembly language instruction. You'll notice that objdump uses kind of slightly different syntax. For things like constants, it will use this pound sign to indicate that it's a constant. Don't worry about that difference. If you wanted to write assembly language using that pound sign, you certainly could, but you don't have to. You'll also notice that it chooses to print out some of these constants in hex just because. All right, so far we completely understand what the assembler did. It took that assembly language instruction, converted it to the machine language bit pattern that we expected. Done. Good. Understood. Next, we have the second line. We can do the exact same thing. Again, sort of look at the assembly language instruction. It's a store instruction. Again, kind of, refer back to the reference. Yes, okay, good, bit patterns match. We understand completely what's going on. Next line. This is an ADR instruction. What is going on here? This seems like a very simple bit pattern to be corresponding to a ADR instruction. In particular, there's this bit pattern here that's supposed to be an offset of some variable where ADR is supposed to compute the address, given that offset, load it into a register, and kind of go on from there. Now, here's the problem. What we wanted to do is we wanted to compute the offset of this message that we're about to printf out. But that's way off in some RO data section that the linker is going to mix and match and shuffle and stuff somewhere in memory. The assembler doesn't know where it's going to end up. The assembler fundamentally can't know where message 1 is going to end up in memory. And it can't even know the offset between this instruction and where message 1 is going to end up in the final executable. Because, as far as the assembler is concerned, there may be all kinds of other .o files that'll get linked in. RO data might have, a bunch of stuff from somewhere else that gets concatenated into the whole thing. It just doesn't know. And so the assembler fundamentally can't generate the full machine language representation of this instruction. It doesn't have enough information. Who's going to have enough information to do this? The linker. And so the assembler is going to write a little memo to the linker saying, hey, help. And these hey, help memos take the form of what are called relocation records. So when you use obj dump, they get included at the appropriate location relative to the assembly language. In reality, they're kind of stored separately in the .o file. But obj dump kind of looks up, which instructions they correspond to and displays them in this way so that you can sort of, match the relocation record to the instruction that it's going to be operating on. So this first relocation record looks like a bunch of gobbledygook. Let's try to decipher it. So first, there's a 8 there. That is the hex value of the offset of the instruction to which this relocation record applies. Simple enough. We have R for relocation. We have AArch64, just so the linker knows to apply the rules for the correct machine language architecture. It's kind of just a cross-check, a double check. And then there's information about what kind of instruction the linker should expect to patch and how. In this case, it says ADR. So this is going to be an ADR instruction. And the linker knows, how to fix up ADR instructions, how to fix up BL instructions, how to fix up, all kinds of other instructions. And this is just telling it, apply the rules that you have hard-coded in for ADR instructions. And what are you going to put in? Well, you're going to put in a 21-bit offset, because that's what ADR requires. And what offset is it? Well, that's this thing on the right here. It says, when you figure out where you stashed the RO data section of this .o file, find that memory address, and compute the relative offset of that memory address relative to wherever you happen to stash this instruction. So do that calculation for me, Mr. Linker, or maybe Mrs. Linker, or maybe non-binary linker, and patch the instruction accordingly so that it contains the correct offset. Okay, and all of these weird rules that, some bits go here, some bits go there, the linker knows about all of those rules because it knows about the ADR instruction on this AArch64 architecture. So the linker is going to be able to, comply with this request. All right, next we have a function call, a BL instruction. We're going to call the printf function. And at this point, the assembler really has no idea where that's going to come from, where it's going to get put in the final executable. So in order to compute this field in the BL instruction, what the assembler would have needed to know is, where is printf going to be put relative to where is this instruction going to be put? Again, the assembler doesn't know that, and it has another relocation record, which is basically another memo to the linker. Dear linker, please patch the text section at that offset, patch in a now 26-bit signed offset appropriate for the function call, or BL instruction format. And how do I compute? How should you, the linker, compute that offset? Well, figure out where you put printf and compute its offset relative to the current instruction. Yes? Program counter, the current location of the instruction. Yeah. Okay, great. Now we have another BL instruction, this one corresponding to getChar. And as we noticed at the very beginning, the bit pattern, the machine language pattern created by the assembler, is exactly the same as for printf. Because the bit that the part that the assembler could create on its own is just the BL part, and it doesn't know where either printf or getChar are going to be put by the linker. So the part that the assembler could generate is the same, but it has a different relocation record, right? So the relocation record says patch this instruction, except patch it with wherever you happen to stash getChar. And so at this point, the machine language instructions are the same, but after the linker gets done with them, they will be adjusted to be different and correct. Okay, so that's how this communication between the assembler is going to work. Next instruction, we have a compare instruction. So let's try to decipher this machine language bit pattern. And here, we have to remember this concept of aliases for instructions. So compare, there's really no such instruction as compare. It's a shorthand for a subtract and set condition codes and put the result in WZR, which means throw the result away. So this machine language instruction is really going to be a subs instruction. And again, we can go back to the reference, figure out what are all of the different bits and pieces of a subs instruction, and verify that the assembler generated it correctly. And now here's the interesting thing. There's also a big fat offset in this instruction format. Wrong thing. In this case, this is an immediate value. It corresponds to hex 41, which is a capital A. That's the constant that was in the instruction. Nothing clever yet. This is the one that's clever. This is a conditional branch instruction. For whatever reason, objdump likes to write it with a dot, branch dot not equal instead of just a BNE. Don't worry about that difference. Write it this way if you prefer. Write it without the dot if you prefer. Here's the clever bit. Conditional branch requires an offset. The offset is the offset to a label in the code. But the label that we're branching to isn't way off somewhere else where the assembler doesn't know about it. It's not like printf, which is way over there somewhere, I don't know. It's actually the label of an instruction in this same section. So as the assembler was going through and figuring out, do I know the address of this thing called skip? It looked through the assembly language code it has access to and said, yes, aha, skip is actually that instruction right there. And so what it can do is actually compute that offset, stuff that offset into the instruction, following our magic rules about, implicit zeros at the end of a branch instruction, at the end of an offset in a branch instruction. But it can actually generate this function completely. So because it knows all of the information, it doesn't have to write a little memo to the linker to ask it for help. Okay? So assembler does what it can as long as it has access to all of the information to fill in the bits and pieces of the machine language instruction. It's only when it doesn't know what to do that it has to stop, write a relocation record, ask help from the linker. All right, here's another ADR instruction. The only kind of interesting and clever thing here is the location that it's going to use to fill it in. It's not just at the beginning of the RO data section, it is at some offset within the RO data section, but that's fine. I mean, the linker certainly can do an add to, figure out an address somewhere within the RO data section instead of at the beginning of that section. No problem. Okay, and the rest of this is going to work, very, very simply, right? So, your turn, think about this. What do you think this relocation record is going to do? Well, again, pretty much what we saw before. It's going to patch this BL instruction. The offset that is going to be used is again the offset between this instruction and wherever printf happens to live. Does that mean that this will get the identical machine language instruction as the previous call to printf? Think about that. Once the linker gets done with it. What do people think? Yeah? No? Why? Right, even though printf is going to live at the same place, the instruction is at a different place, so the offset is going to be different. Yes? The 26 in this relocation record is just sort of an indication that it's going to be 26 bits worth of offset, just because that's what that instruction format takes. All right, so you can, as an exercise for yourself, go through and verify that this machine language corresponds to those instructions according to the information we have in the reference materials. So all of that works. So that's the assembler. Now the assembler, yes? Yes, yes. So when we looked at this, we have some sort of offset within RO data. So the assembler laid out the message 1 and the hi, I forget what it was called, it laid those out within the RO data section, or at least its share of the RO data section. And so the assembler generated that hex E offset and passed it on to the linker, because that's where it laid out that hi message relative to the beginning of its share of the RO data section. Yeah? Yes, yeah. Yeah, so the linker is going to put together a big fat RO data section consisting of the fragments that it got from all of the OBJ, all of the .o files, but within each of those fragments, it's going to leave the order the same. Yeah. Exactly, yes. It's referring to this .o file. Yes? Yeah, so the way to think about it is that within a .o file, you have sections of data that are going to end up in the different sections of the executable file. So there's a little bit of RO data within this .o file that's going to end up somewhere within the RO data of the executable, and in turn, that's going to end up somewhere in memory. And similarly, this .o file has a section of text, .text, that's going to be concatenated with all of the other text that's going to be linked in, that is all of the other executable code, and that's going to get put somewhere in memory. So it's up to the linker to keep track of, okay, at this location of memory, there is some data that ultimately came from RO data section of this .o file. And the linker does keep track of all of that, at least long enough to do all of the relocation. Yes? Can you put labels above RO data? So all of the data that you declare, all of the labels that you have to end up in some section, right? I mean, that's how the assembler and the linker operate. That everything is in its own section. So you need to decide what is the section. Is it RO data? Is it data? Is it text? Is it BSS? If you try to put a label outside of a section, I actually don't know whether it's going to throw an error or whether it's going to, by default, assume one of those sections. You should try it out. Yeah. All right, so let's move on to the linker. So assembler writes a .o file corresponding to a single .s file, which might have been produced by a .c file in turn by the compiler. The linker is going to read all of that information, do some shuffling in memory, and going to do two primary tasks called resolution and relocation. Relocation, you can already guess what that's going to mean. It's going to mean patching up all of those instructions according to the relocation records we have. Resolution is the prerequisite to that. It's making sure that if you referred to something called printf, eventually the linker is able to find something called printf. So this is kind of the spell checking phase, if you will. So, if you tried to call something called prontf, eventually the linker is going to say, I don't know what that is. I don't know where to get that from. And what are the options the linker has for finding all of these labels you want it to use? Well, it can find them in the .o files that you put on the command line, or it can find them in the standard C library. So standard C library, big, huge thing. It contains, dozens, hundreds, for all I know, thousands of functions. The linker is going to look up which ones it actually needs to use in order to produce the executable for your program. It doesn't just grab everything in the standard C library. It's actually a little smart. It only grabs what it needs from the standard C library so that it can staple it onto the end of your code. So that's called the resolution phase. And for our sample program, the thing that it's going to do is figure out it needs something called getChar. OK, great. I found it in the standard C library. I need something called printf. OK, great. I found it in the standard C library over there. It's going to automatically include some sort of startup code. And one of the unresolved labels in that startup code is going to be main. So in order to produce a successful executable that includes that startup code, which it always does, it's going to need to find main somewhere. And because main isn't in the standard C library, it's better find it somewhere in one of your .o files. OK, so it's going to kind of pull in everything that it can so that it has all of the information that it needs to produce the final executable. Then it's going to lay it out in memory. It's going to actually say, all right, here are the 17 bits of RO data that I need. I'm going to smush them together and put them at that address. Here are the 23 bits of .text that I got. I'm going to smush them together and put them at that address, and so on and so forth. And then it's going to go to the relocation phase, where it goes through all of the relocation records and kind of does what they say. carries out the requests that the assembler made of the linker. So again, we can run the linker. We can now run obj dump, and we can see exactly what happened. So we have RO data first that we can look at. And when we look at RO data, we see that our RO data from the .o file that we had wound up, somewhere in that RO data section, the grand unified RO data section. Notice that over here, we no longer have offsets. These are now going to be actual locations, actual addresses in memory. And so the linker is going to use these actual addresses in memory to do the relocation on the code. So again, we can run objdump with disassemble and relock. The relock flag we passed there just to verify that there aren't any relocation records left. Hey, look, Ma, no relocation records. Again, we have kind of addresses, not offsets. If you actually do this on an executable file, eventually you'll find your code, but, dot, dot, dot. It's going to be stuffed in amongst a lot of other code that the linker had to bring in to implement things like printf and getchar and all of that startup code. All right, so no relocation records. And we can kind of go through and verify what the linker did with them. By the way, if you haven't heard of the story of Emily Hale and T.S. Eliot, kind of really interesting little story that cropped up a couple of years ago. Turns out that T.S. Eliot, famous English writer, sent a bunch of essentially love letters to Emily Hale. They were not published until, I think it was last year, maybe 2 years ago, and they're in the collections of the Princeton University Library. Fascinating story, look it up. All right, we had a relocation record for this ADR instruction, and what the heck did the linker do with that? All right, well, the instruction bits are still the same, but now there's an actual offset within this instruction. So we can look at that offset, decipher what that means in binary, a couple of bits of the offset over here, smush it all together, blah, blah, blah. Here is the offset that we're dealing with. Hex C8, right? That corresponds to that number. All right, so where is this instruction? Well, we can go back and we can look, here is the address of that instruction. We can go back and look in RO data. Where did message 1 end up? 400720. All of this is hex, remember. And so we can go back and actually do that subtraction. 720 minus 658 is hex C8. Whew. Saved again by math. So the linker actually did the right thing. It computed these addresses, computed the offset, stuffed it in the machine language instruction, done with this relocation record. And similarly, we can go through all of the other relocation records that we had. Here was one that involved printf. And so we ended up with some offset that the linker chose to put in there. And we just needed to go through the rules. Take those bits, add the 2 implicit bits at the end, treat it as a signed 2's complement value, compute what it means, and it's the negative of 17C in hex. Figure out where printf was by looking in amongst those ... dots that I highlighted on the previous slide. Do the subtraction and verify that the offset is indeed what you expected. So seems like magic, but actually no magic, just math. And you can go through and verify that the math is correct. And everything else is going to be similar. We have a couple more function calls, and in particular, we can sort of look at this case that we talked about before. Here is a branch to printf. Here is its machine language representation. Here is the other branch to printf, and it has a different machine language representation, accounting for the fact that even though printf is at the same place, it is at a different offset. Okay, so questions on this. Questions on what the linker does and how it does it. Yes? Does the linker start at address 0? It typically doesn't. On this machine, it seems to start at 40000, just because. You typically don't want actual good stuff starting at address 0 in memory. And the reason for that is when you dereference a null pointer consisting of a bit representation of all zeros, you would really like to have that generate a seg fault. And so the linker kind of helps you out by putting the good stuff, the stuff that you're actually allowed to access, away from 0. And so when that gets loaded up as an executable and you start running it, the memory pages corresponding to address 0, and in general low-numbered addresses, get set to illegal. Don't, no access. You're not allowed to read it. And so then the chip, when you try to dereference a null pointer, is going to look it up in all of its page tables. In its page tables, it's going to discover you're not allowed to read from that page or write to that page. And it's going to, throw eventually wind up with a big fat seg fault for your program, which is a good thing. Again, program crashes are a good thing because the alternative is that the program silently corrupts memory, and that's much harder to debug. More questions? Yes? Yeah, so it's always relative to the current instruction. So when we look at this call to getChar, the offset within that instruction always has to be relative to where that instruction lives in memory, right? And so you always have to be going relative to the beginning of this instruction. Does that kind of answer your question? Yeah, so let's go back and look at this call to printf, right? So the offset there, we know that the BL instruction, this BL instruction, lives at this address. We know that printf lives at this other address, and so we subtract those two addresses, and that's going to be our offset. Yeah. Mm-hmm. All right, so summary. We've looked at AR64 machine language. All instructions are fixed length, 32 bits long. The formats have conventional locations for opcode, registers, immediate values, offsets, things like that. And today we looked at kind of these little memos that the assembler writes to the linker and what the linker does with those little memos, the relocation process. And that's it for the course. So that is the end of the content. Lectures end today, precepts end today. Assignment 5 is due today. All right, not quite the end of the course. Assignment 6, due on Dean's date. The nominal deadline is 5 p.m. If you have late days available to you, they only get you to midnight of that day. Beyond midnight on Dean's date, you need permission from the aforementioned Dean to get an extension. Final exam, we sent out an announcement yesterday. It is going to be online and not in person. The logistics just started getting too messy, too complicated. People's stress started getting off the charts. It's going to be online, 3 hours. We'll figure out a block of dates. Watch for announcements. Remaining in-person event is going to be a review session for this course. It is going to be 2 weeks from today. That is Thursday the 16th. Usual time, usual place. Send questions ahead of time. It will be recorded so you can watch it later. And there will be office hours. And beyond that, thank you for attending 217. We hope it has made you a better programmer. And the end. All right, thank you.